record on this, and then press record on.
Yeah, on Zoom.
Okay,
I can turn off the light in the front so I can see that.
Sweet. Record. Do you want me to record to the computer or to the cloud?
A cloud.
Oh, there's 3 participants. Sweet. All right, maybe I move this a little bit this way so that people can see me a little bit. All right. Okay, I think this is good. All right, welcome to my talk. My name is Vivekanand, as probably all of you know in person, and I'm a research scientist in the Ashton Graybiel Spatial Orientation Lab. And today, the name of my talk is the Perfume of Potential Mathematical Collaborative Ideas in Spatial Disorientation Research. And I chose this topic because, as you may have seen from my abstract, I don't do anything that's very math heavy. Most of what I do is sort of like behavioral, human stuff. But I have this deep desire, you could almost say it's like a pang of desire, to bring in these like really cool mathematical ideas. And so really today is mostly about me sharing all these different projects that I do. And at the end of each of those projects, I'll be like, here's a collaborative idea that we all could potentially work on together. And wouldn't it be epic if through this sort of meeting or seminar, something comes out of it? And this image, which I drew several years ago, sort of depicts this dream. Here we are in the center, all 3 or many of us just doing a little bit of science, sharing together this thought bubble. And then surrounding us is all of these adventures. And I'll sort of talk about how maybe we can do adventures that go beyond just math and science as well. So, in today's talk, I'll go first over my paradigm and describe how I create a spaceflight analog condition here on Earth in a lab. Then I'll talk about the concept of angular path integration and explore some mathematical, computational models of the vestibular system. Then I'll sort of talk a little bit about how, metaphorically, I explore these ideas of attractor points, homeostasis, phase transitions, words that hopefully kind of excite, kind of seduce some of you, maybe. And then I'll talk about the next branch of my research, which is human augmentation. I will then dip a little bit into anxiety and Hilbert transforms, and then finish off with this idea of like, how do we party? Bringing in concepts of mathematics and biology.
Sorry, you might need to share your screen on Zoom.
Oh. Escape and Zoom. Oh yeah, share screen. Share. All right, cool. Thank you. So, okay. All right, so chapter 1 is my paradigm. So, the general storyline that I usually give for these types of things is that imagine that you are an astronaut on your way to Mars. You spend months and months in 0G. And by the way, in 0G, if I blindfold you, the concept of up doesn't even exist. And then comes a day when you have to land upon the surface of Mars. And what we know is that in that gravitational transition, as you go from 0G to Mars G, astronauts will become susceptible to spatial disorientation. And this is a word, or 2 words, that I'll use often in this talk. And spatial disorientation means that you lose sense of which way you're oriented, of where you are, of where up is. And you can imagine that something like that could be quite deadly if you don't know where up is as you're trying to land this spacecraft onto the surface of a planet or the moon. And just to emphasize how big of a problem this is, forget the unknowns of space exploration. Here on Earth, one of the leading causes of fatal aircraft accidents, accidents where pilots are dying, is spatial disorientation. So this is vastly still unknown. There's still a lot of things that we need to understand about when it happens, why it happens, and what kind of countermeasures can we do. So, the next question is like, how do I create a spaceflight analog condition here on Earth in a lab where people cannot rely on gravitational cues, similar to how astronauts cannot rely on gravitational cues? And the way that I do it is I strap people into this beast over here. This is not my spaceflight condition. This is sort of what I call the Earth analog condition, the upright condition, the control condition. I'll describe it first. So I strap living human beings into this machine. They're blindfolded. Okay, and I chose inverted, or we chose inverted pendulum dynamics because to a first approximation that represents human balancing, it represents an unstable vehicle, and what you'll also sort of notice here is that there are crash boundaries. So if you go too far, about 60 degrees to either side, the machine will stop and then it will automatically reset you and the trial resumes. So now what I do is I ask people to grasp that joystick and balance to the best of their ability at that 0 degree point. Which in this case also aligns with gravitational vertical. An interesting side point is that this by itself is a fascinating sort of experimental paradigm because here I am trying to balance myself, but I'm balancing myself without things that I usually use to balance myself. I'm balancing without my legs, without the biomechanical properties of my legs, without all the reflexes that typically we use to balance. So one important question that this paradigm alone sort of asks is, what is sort of like the central processing of balance control when you take out all these peripheral mechanisms like reflexes? Also here I'm wearing my predator prey pants, which I designed and then my mom sort of sewed. So in terms of sensory information, what sensory information are people receiving? Because they're blindfolded, they get no visual information, and because they wear noise-canceling headsets, they get no auditory information. Primarily the information that they're getting is through their vestibular system, and to a secondary extent, their somatosensory system, the touch receptors on their skin as they push against this machine as they're trying to balance.
Could you say something about, so I guess you're quite good at using this joystick, I'm guessing.
Yeah.
You're an expert at this, but then you're also like testing this on people who don't have experience. So how do they usually?
Yeah, you have predicted what will come in the future. So thank you. And that'll be in like 5 or 6 slides. Yeah.
And our question is, why did you remove auditory stimulus? Do you think you could use some auditory stimulus to balance?
Yeah, so ideally what I want to do is just focus on the vestibular system, and the reason why is because, as I'll show you in a second, my spaceflight condition does a really neat trick where the vestibular system is behaving in an unusual way, you could say, that causes disorientation. And so I try to take out all the other cues just to be like, this is because of the vestibular system. There was a grad student, Lila, in the lab who did give auditory information to assist in the process of balancing when someone's disoriented. And it does help a little bit. Also, the directors of the lab, Jim Lackner, I think Paul also, have done things with auditory cues, where I think they've had like rotating auditory cues, and they show that even if a person's, and maybe Joel or Albert or Avi, you can correct me if I'm wrong here, but that sort of induces a sense of motion in a person. Is that correct?
And motion sickness also.
Okay, yeah.
Which is something you didn't mention. They get out and walk on Mars, they're going to be quite susceptible to motion sickness.
This is true. This is true. Yes.
Which I can personally attest to.
Yeah. So thank you. Yeah. All right, cool. So the vestibular system, just for those of you who may not know, is located in your inner ear, and usually to explore it, I like to take a magic school bus ride that goes right into the inner ear. And once inside, you'll find that the vestibular system has 2 components. The first are your semicircular canals, and these are filled with fluids and have little hairs inside them, and they detect angular acceleration. And you could say to a certain extent angular velocity. And this is during rotation. So if you're rotating like this, or like this, or like this, these will all activate different semicircular canals. We've got 3 of them all at sort of 90-degree angles, and a set of them on each side of your head. The second component of the vestibular system are your otolith organs, and these are fine little hairs that are suspended in gelatinous material adorned by crystals, and they detect linear acceleration. And really, for today's presentation, the main thing that they detect is tilt from gravitational vertical. So the more that you tilt, the more these hairs will deflect. And in a way, then, you can really get a pretty good sense through gravitational cues of where you are in reference to the upright. So, in this paradigm, because people are balancing in the upright, and the upright is where the balance point is, you have a very good sense of your position because your otoliths are telling you through gravitational cues how far away you are from that balance point. And your canals are giving you a mix of sort of acceleration and velocity.
So is this affected by other types of acceleration if you move?
Is this affected, you mean like your vestibular system?
Yeah, the
The otoliths, yeah. So other types of linear acceleration will affect it too. So for example, if you're in a car and you begin to accelerate forward, these hairs will sort of deflect backwards. And one interesting sort of phenomenon is what they call the tilt translation ambiguity, which you can actually try out when you're in a plane. So if you're in a plane, you don't have a lot of rich visual cues. Maybe if you're sitting by the window, you close your eyes, and then as a plane begins to accelerate forward, you can take your hand and sort of indicate how far you think you're tilted. Because what's happening is as you're accelerating, those otolith hairs are being pushed back. And usually what's going to happen is you'll estimate that you are tilted way more than you actually are, because then you look out the window and you're like, whoa, I'm actually not tilted as much as I was feeling. And I think in the early days of like the aircraft carriers, these jet planes, as they would accelerate, people didn't know this, and so they would feel like they're going up and they were not, and they push the control thing down and they smash into the water.
So as you're falling and accelerating towards falling on your device, gravitation is telling you you're tilted, but acceleration is telling you you're...
So so when you're sort of going this way, you have two components. One will be the gravity component that's sort of deflecting it this way. But yeah, you'll also sort of have like a tangential component of your like acceleration, which will also be affecting the hairs. At one point I had calculated both of these, and the magnitude of effect from the tilt is way more than sort of like the tangential component that you get from acceleration, because accelerations are not like...
accelerate too much on this device.
Yeah. Cool. Thank you. Yeah, great question. So then, in my second condition, what I do, which I call my spaceflight analog condition, I take people and I tilt them onto their backs. And now all the dynamics are exactly the same. It's still inverted pendulum dynamics. You still have to try to stabilize yourself right at that center point and use your joystick. The reason is, so you may be like, why do you call this a spaceflight analog condition? So if you remember, in the upright, in the Earth analog condition, the more you tilted away from the balance point, the more the hairs deflected, so you had a good sense of where you are. But on the back, if you're at the balance point, those hairs just point down saying, hey, you're on your back. And if you're really far away, those hairs again just say you're on your back, because you're no longer tilting relative to gravity. So what happens on the back is that you no longer have, through gravitational cues, a sense of where that balance point is. You just don't know where you are. And this is like the trick that I'm using to make this into a spaceflight condition. You still get reliable information through your canals about acceleration and velocity. And the reason why I call it a spaceflight condition is, again, like during that initial descent, when the gravitational cues are very weak, people are not going to have reliable gravitational information to exactly know where up is or where that balance point is. And it's very similar to how people experience, or what they experience when they're on their back. Okay, so here's like the first set of data. Now, I do a lot of like mathematical, nothing too impressive, a lot of like metrics to quantify learning. I've got things like this, which I'll describe in a second, but I also have analysis with phase plots where I look at like the phase relationship between like position and velocity and joystick deflection. I use things like the stabilogram diffusion function, which is like mean squared displacement as a function of different time windows to look at like what people are doing. But for right now, the main thing I'll just so you get a general sense of what's happening is this summary metric of the standard deviation of angular position. And again, all this means is the greater your standard deviation of angular position, the greater sort of, you could say, the variability around that balance point. And if you get better, then you become a lot more focused. There's less variability around the balance point. And this is the people in the upright roll, or the upright condition, the Earth analog condition, where they have a good sense of where they are. So you see this very classic learning curve. In my experiments, I have 5 blocks of experimentation. Each of those blocks has 4 trials, and each of those trials are about 100 seconds long. But really, all they're trying to do is balance themselves for about 40-50 minutes. Okay, so this group of people learns really well, but now let's look at what happens if you bring people who are in the spaceflight analog condition, where they don't have reliable gravitational information. And what we find is, and again, the literature would have predicted people would perform worse, but they never would have predicted that the magnitude of their inability to perform would be this huge. And I'm going to talk a little bit more about that when I get into the path integration section. But long story short, what we find is that these people are not only bad, they're 2 times as bad. And not only are they 2 times as bad, collectively as a group, they're not able to reduce the standard deviation of angular position. So you could imagine being in this machine for like 40, 50 minutes, trying your best to sort of control it and not being able to, and just accumulating this huge amount of frustration. And later on, I'll sort of talk about what I think the links between anxiety and frustration and things like that are. So people show very minimal learning, very poor performance, very high rates of hitting that crash boundary. Now this graph is not going to evoke any emotions in you. So I tell you that, yes?
Is it significant the increase in standard deviation of the standard deviation?
I'm sorry, what's that?
It seems that the standard deviation doesn't move, but the fluctuation around the standard deviation on the back row is increasing.
You know,
quite a lot.
It's a really good point. I don't know. I feel like I must have looked at it at some point, but I don't know if the standard deviation of angular position is increasing over time. But if I had to tell you intuitively, I would say yes, it is. And I'm going to talk a little bit about that in about like 5-6 minutes when I talk about the individual differences that I see in this group. It is a great observation.
You will probably cover it.
Yeah.
But is it that people realize they fail and maybe they get frustrated, as you say, but maybe they try heuristics?
Yeah.
Or they try new strategies? Do you see that?
Yeah, definitely.
Like I'm gonna just oscillate. So
So
I never move and I oscillate deterministically. So
you're seeing into the future. So like what ultimately I'll talk about is that what happens here is that some people converge towards a strategy that's optimal and other people converge towards a suboptimal strategy. And that's sort of what's driving this huge amount of variability that you see. So I will, in 5 or 6 minutes, I will hopefully satisfy that desire of yours. So again, to evoke your emotions, and for those of you that haven't been in the machine, and it's probably only 3 of you here, you're more than welcome to it. I can put you in it and you can sort of experience it. 90% of people are just like completely baffled and they're like, this is very surreal, I have no idea where I am. 100% of them show in their data. About 10% report very unusual illusions, like they feel like they're completely upside down when in reality they're on their back. So it's just kind of interesting, again, how the brain is trying to patch together reality when one critical piece of information is missing. So this is like a aside, but again, one that's supposed to be mathematically interesting, which is that in the skilled motor learning literature, often what they say is that this variability may have structure within it. So just don't be like, all right, the standard deviation of something is big. Look into that data and maybe you'll find a pattern. And sure enough, in my data, I sort of find that. So this is raw data. This is on the x-axis is just time. That green line is the target, the 0 degree point. This is people in the upright. This is just one person actually in the upright. A representative participant, and it's trial 20 at the end of the experiment. And the black line over here is the angular position. So this person, she's going a little bit to the right, a little bit to the left, back and forth, doing a great job, minimal oscillations, mastered the task. Now we take a look at what happens when I put her in the spaceflight condition on her back, and it's kind of phenomenal because what you see is that she starts off near 0 degrees and then she gets further and further away. Here she's oscillating at 20 degrees as if that were the balance point, and she gets further and further and further away until suddenly she hits the crash boundary at 60 degrees, and all of a sudden she says, oh my God, I was very surprised, I had no idea. And pretty much every participant in the early times they hit these crash boundaries are completely, just in absolute surprise that they have traveled such a far distance. So this is the pattern, positional drifting, that I see in my data set, and every single person shows it to a certain extent. And this brings us to the topic now of angular path integration. So within the literature, the idea is the following. What the literature would say is that, okay, they're on their back, they don't have positional sense, but they still should kind of be able to do this task. And the reason why the literature would say that is because there's this idea of angular path integration, circuits in your brain that can take velocity information and integrate it over time to make an estimate of position. And this is something that's not theoretical. It's been supported by evidence. We know we have neural circuits that are devoted towards this task. So, one would imagine that, okay, fine, you're integrating velocity over time. There's going to be some sort of error accumulation that may happen as time goes by. But I've spoken to people who've developed some of these models, and these models are kind of complicated, but they talk about how information from the otoliths and the canals are sort of integrated and woven together, and they also are like, you know what, I don't think my model would necessarily predict such a fast rate of disorientation, and certainly not be able to predict what I see in individual differences, which I'll talk about in just a moment. And so what I'm trying to get towards, maybe towards the end of this section, is that one collaborative space we could explore is looking at some of these mathematical and computational models and seeing how does my data set, how can we update it or how can we improve it. So coming back to the data, I ran another experiment where I put people in the spaceflight condition, and now while they're trying to balance themselves, I said, press a button whenever you perceive like you're at that 0 degree point. And so again, here in this data, you can see the person starts off at 0 and they get further and further away. They're just sort of drifting and drifting and drifting and drifting. But the question is, are they perceiving that they're drifting? Or do they perceive that, oh, I'm getting further and further away, I just can't control it? And what we find in the purple dots here is that the further that they get away, they continue just perceiving like they're at the 0 degree point. So here the person's oscillating at 30 degrees. They actually feel like they're at 0 degrees. It's really sort of like astonishing. Over here, they're at the jaws of death. They're at 50 degrees, right about to lose control, and they're pressing the trigger as if, oh, you know what? I'm right at the 0 degree point. Everything is safe. Everything is good. So this is kind of extraordinary. It's kind of like, when you experience it, it's very like jarring when all of a sudden you're like, oh my God, I just hit the crash boundary. I wasn't, yeah.
I have a feeling that this person is feeling that they're moving because the joystick only goes one direction.
Yeah, some of these people are not
They're
even...
never compensating. I mean, they feel they always fall on the same side.
Yeah. So what they're doing, you'll see sometimes this in the upright as well, where they have a good sense of what they're doing, because what they're feeling like they're doing is they're catching and falling. Catching and sort of falling. So they're sort of falling, they catch themselves, and then they push themselves off. And they feel like they're always returning back to 0 degrees. But with each of these returns, they actually don't come near 0. They get further and further and further away. Yeah.
So, I don't want to precede something that you're going to say maybe. But did you correlate the deflections of the joystick with the derivative of the angular position?
Did I correlate with the velocity, the joystick deflection?
The derivative of acceleration.
Yeah, so whether they're responding to velocity.
To changes in velocity.
To changes in velocity. I don't think I have specifically that way. I may have gotten around to it one way or the other, but yeah, I'll look into that. That's good. So correlate the joystick deflections with
the derivative in time.
Yeah.
Anyway, the joystick deflection with the derivative in time.
Yeah.
Okay.
Oh yeah. Oh, cool. Thank you. This is the reason for doing this. So then, continuing to dig into this like perception thing, what I did is I put people in the machine, and now they're just being passively moved. They have no control over the machine. And what they're trying to do is press a button every time they feel like they're back at that start point. And this is a sum of sines thing. So the blue line is just a sum of sines. This faint black line is a 0 degree point, and this is in the upright. So they know where they are. Basically, all they're trying to do is press a button every time they feel like they're upright. And you see that this person is quite accurate with this task.
What is the pink? Did you say that?
Oh, the pink is, I think, the velocity.
Oh, okay.
Yeah. And then you put the person on the back, and again, this is where things get really bananas. This gets really unusual. So, in the beginning, they're very close to the 0 degree point, and then just within 10 seconds, this person's 50 degrees off, But then what is so bizarre is that after 40 seconds, they no longer press that trigger button. And so the question becomes, why? I even asked them, what's going on? Have you fallen asleep? And they're like, no, I don't feel like I'm asleep. I feel like I'm 180 degrees away. I feel like I never come back to the 0 degree point, even though they are multiple times here. And what's really, again, mind-blowing is that I go in this machine knowing everything about the machine, that it only operates between 60 and negative 60, but I feel these rotations where now I'm 180 degrees away, which I know is physically impossible, but that's what I'm sensing. So this is something, again, that none of the vestibular models right now are able to predict, especially when you then contrast it to another representative participant who does great in the upright, but the moment you put them on the back, this person is like, it's a machine gun, and they're just like, bah, 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 bah. And they're shooting this, but they're always missing the 0 degree point, but every little motion they sort of perceive as if they're back to that 0 degree point. So this is very fascinating, very unusual. It sort of expresses the individual differences that exist and how limited some of these models may be in being able to address this. So both participants experienced the exact same profile, wildly different perceptions. As I said, no model right now can predict this. And one reason for it may also be is that no model really has data like I do with humans that can sort of in real time be able to express where they think they are. Most of the things that people do are just these single cycle rotations, and then they say, how far do you think you've gone? And in a single cycle, people are pretty accurate actually in telling how far they've gone. It's usually when you've got these multiple sort of movements that the error just goes completely bonkers. Okay, so before I sort of put the collaborative idea here, the other thing I kind of want to say is that people have looked at angular path integration in other models. So people have looked at it in flies, where they glue a fly onto a stick, and then they put it on this hovering ball, so that as the fly walks, the ball sort of rotates, and then the fly is looking at this virtual world. And so as the fly is sort of walking, the virtual world is moving. And what they've sort of noticed is that when there are no visual landmarks, when everything is completely dark, this fly also exhibits this sort of angular path integration, drifting in angular path integration, which is kind of interesting. And in my condition, when you're typically moving, you're getting information from your canals that you're rotating. The landmark are your otoliths that sort of calibrate the error that your canals may be accumulating. So when I take that landmark away, it's kind of similar to how they take the landmark, the visual landmark, away here. There are also computational models on this. This is the bump attractor ring model. And again, in these sort of computational models, if you take away the landmarks, you begin to see that the system drifts a little bit. And so it's kind of cool. And some of these models are simulating sort of head direction cells and grid cells and sort of up to this level of angular path integration. And they've even done stuff with freely roaming rodents, where they're sort of walking around in a big arena. And again, in the arena, if you take away the visual landmarks, you begin to see drift in their grid cells. So the collaborative idea is, again, the easiest collaborative idea is we just get together, we chill, we have a good time, and then we review some of these computational mathematical models, and we sort of piece together a storyline that goes all the way from flies to the work that I do in humans. And we could do a small event at Brandeis, or I don't know, write a paper or make a small video. I think it'd be kind of interesting because I don't think that storyline exists. And the other thing we could do, which would take a bit more effort, is try to update some of these vestibular models using my data, maybe run a few more experiments. And I think that would be kind of fascinating because it would definitely add on to the field. Okay, the other sort of side story that I have is I've been collaborating with this guy at MIT Media Lab who does galvanic vestibular stimulation. This has been an idea that's been around for a while, and you just put these two electrodes behind their ears, and then you just send an electric current. And what it does is like a rough hammer, it just sort of stimulates the entire vestibular system. And in theory, what you can do is if someone's blindfolded and they're walking, and you stimulate one side, you can make them veer off in one direction or another without them really knowing. So you can sort of induce a sense of motion in people. And one of the ideas that we are thinking about, although it may be very difficult to reach, is you put people in the spaceflight condition where error is accumulating, and then you just trickle in some current to sort of fix that error. But all of this will again require mathematical and computational models of each individual's sort of sense of self-orientation. The other really fast mathematical idea, which may appeal to some of you, is in the skilled motor learning literature, not only do they say look at the structure within the variability, but they also talk about the idea of looking at variability and how it changes in the task relevant and the task irrelevant axes. And so here's an example. This is from Dagmar. I took a course with her, which is why I know some of her work, but it's kind of really cool stuff. So what they do is they have sort of this. They take the person's in a virtual world, and they're trying to throw a dart. And then in real life, they're holding some sort of handle or something, and they sort of move the handle and let it go to represent throwing the dart. And so what she has access to then is just position of when the handle was let go and the velocity when the handle was let go. And with that, she can mathematically construct what she calls a solution manifold So this gray sort of rainbow over here are all the position velocity pairings that lead to successfully hitting the bullseye. And then she can look at the variability and how it changes as a person learns, and does it change, within the task relevant or task irrelevant axes, and then she has like a bunch of different things that she does. It's kind of cool, and myself along with a bunch of people in the lab have been thinking about, well, how do we develop a solution manifold? Our system is obviously more complicated. We have multiple solutions. If you're at a particular position velocity, you can do one big joystick deflection, or you can do a bunch of small ones, and they'll both bring you to the solution. So how do you deal with that? There's also a temporal component, because as psychological creatures, humans will often react to what they've done in the past. And so that information has a valuable amount of information to it. But again, there are different options of approaching this. Abhijit has tried to do a statistical thing where you take the position, the velocity of all the data, or maybe just the people who perform really well, and see what they're doing with their joysticks and sort of create an averaged manifold. And he does more complicated things than that, but that's sort of one general way of exploring it. Alberto and Paul have done some really cool things of looking at the inverted pendulum system itself and looking at that and how do you create a manifold based on that. One thing that I'm interested in is how do you create a manifold without even knowing the details of the system? What theoretical things do you need to know to create that? What experimental things do you need to know? And then what kind of things do you need to create if you have multiple solutions in the system, or if you have a temporal component? Or, I've been doing projects with machine learning and deep learning, and these essentially are creating multidimensional, regression type manifolds. Can we sort of exploit that and use it to be able to understand and visualize some of these things? Can we generate these manifolds at each time point? And then once we create the manifold, can we use it to characterize optimal control, or look at differences in individual differences? Okay, so the next section is sort of really quickly on dynamical systems viewpoints. I don't really propose that what I do is dynamical systems directly, but I feel like there's some metaphorical things that I can use, maybe some of the favorite words that people like. So, at the core of what I do are oscillations. And so, are there some generalizable patterns or tools that we can use? I can take my trial data, of position and velocity, and then for each time point, I take the position and velocity and I can make a phase plot. And so this is on the x-axis is angular position, on the y-axis is angular velocity. And so, for example, this vertical line across here would be at 20 degrees, what are all the different velocities that people have experienced? There are a number of questions I can sort of ask. One of the things I look at is a phase relationship between position and velocity, and what do people do with the joystick. And I won't go into too much detail right now about this, but if you're interested, I'm happy to talk about it. When you're in the first and third quadrants, your position and velocity have the same sign. So if you then take the joystick and you deflect in the same direction, that will always destabilize. It will always throw you away from the balance point. So I sort of highlight that in blue, and I look at, I make some metrics based off of that. But for now, the main reason I'm showing you this is that if you visually look at it, it looks as if the system is oscillating around a point, which it is, the gravitational vertical. And so you can metaphorically maybe say that the gravitational vertical is like an attractor point, it's like a homeostatic set point. As a human gets further away from it, they have some sort of restoring force or something that brings them back to that center point. And what's interesting is that if you then make a phase plot of the spaceflight condition, you begin to see this drifting in the phase space, which looks like circles that are sort of drifting across the x-axis. And it almost looks like this one attractor point has shattered and sort of spread across the x-axis, and you can sort of look at it like that. And some interesting questions again is that, if you then pitch the person back, so at 0 degrees at the upright you have a strong attractor point, on your back it shatters. The question is, just like in physics sometimes, is where does this phase transition happen where that attractor point sort of breaks and shatters? Is there hysteresis when you go from top to bottom or bottom to top? These are all questions that potentially we could ask, and I'll talk a little bit more about this in the human augmentation section. The other sort of collaborative thing that I thought would be interesting would just be to collect a bunch of examples, both theoretical and in real life, where you have a homeostatic set point that's broken, that's shattered. How does the system respond? What tools do we use? What patterns do we see? And are there any commonalities, all the different ones that we have? I think that would be a really interesting, again, an event or a paper or a video, anything like that. Okay, so we're nearing that now in some ways. Chapter 4, human augmentation. And this is sort of the next stage of what I'm doing, and it's what I've been funded to do for the last year and the upcoming year. And so one proposed countermeasure to spatial disorientation is this idea of using technology to enhance human performance. And so, the way that I do it is, and it's kind of hard to see here, but on the person's arm, I put, these little vibrators, these little vibrotactors. So, on the left arm, you'll have 4 vibrotactors, and on the right arm, you'll have 4 vibrotactors. The more you tilt from the balance point, the more of them will activate on the same side of your body. In a way, it sort of replaces the otolith signal that you had. You now have sort of like a positional information that's being expressed to the skin on your body when you're in the spaceflight condition. And the general question is, does this help? And there's a lot of like cool basic science that I explored, and there are a lot of nuances that I'll sort of skip over. But long story short, what we found is the vibrotactors help. However, they create a pretty significant amount of confusion and conflict. When you're on your back and you're trying to balance, you may perceive like you're here. The vibrotactors may tell you you're over here. It's very like, you're like, wow, what's going on, right? Mm-hmm. And so, I developed training programs. I've taught people to disengage from their inner sense. But one of the dreams has been, what can we do so that these vibrotactors, like the human merges with these vibrotactors, becomes one with them, so that the vibrotactors can actually calibrate this error and actually perceptually make a person feel like they're in the right place. And there are a lot of questions that you can answer about that through the larger umbrella topics of sensory substitution, which I can sort of also answer. The other sort of thing is like, as I'm getting into human augmentation, there are a variety of other things that we can do outside of spatial disorientation that I'm interested in too, such as having very large groups of people that have these things on them and sort of looking at the network dynamics of how people interact and what the network needs to look like for there to be communication that works in an interesting way that leads to emergent properties, you could say. So that could be a collaborative thing too. We get a bunch of these undergrads and then we sort of look at some of these like, small world network or some other network types and see how communication can spread through it and whether we can sort of have some sort of interesting emergent properties that arise from having the arrangement of some simple rules. So that might be an interesting collaborative project if you're interested. What I'm working on now, the upcoming year, is the question of, okay, you're on your back with the vibrotactors, you have this conflict. But what if I take people and I just pitch them up a little bit, so they have a little bit of gravitational information, just a trickle of truth, but it's very noisy, and they can barely detect it. So for example, in lunar gravity, like I just pitch it up a little bit, and then see, do the vibrotactors help? With a little bit of truth, do the vibrotactors now actually help you calibrate and know where you are? So that's sort of like the next stage, and there may be a possibility. So I've talked to the PI of this paper, Marco, who's a cool guy, and what he does in his research is, he has like a VR sort of setup, and in the VR setup, the person is like trying to estimate distance of like a whale in the ocean, and the whale is surrounded by stuff, and it's kind of noisy, and you can't really tell how far away it is, and then he adds a vibrotactile component to it. And long story short, he finds that these vibrotactors sort of enhance the noisy visual information that you're getting, and it sort of is a Bayes-like integration. So anyways, I haven't fully read this paper like in great detail, but if you're interested, the reason I have it up here is that a potential collaboration could be that we try to incorporate some of these ideas into the paradigm that I have, or we get other types of analyses and see how these Q combinations are happening. Okay, this is the second to last chapter, and this is on anxiety and Hilbert transforms. So, long story short, just as Jonathan was saying, you look at this and it looks like the variability is increasing quite a bit. Statistically as a group on this particular measure, and pretty much majority of the measures that I have, the people in the spaceflight condition show very little learning to it, almost no learning. Here there's no significant learning as a group. But the question now is that, are there individual differences? Are there some people that learn, some people that don't? And so what I did is, with Pengyu and one of his undergrad students, we got together, we even ultimately published a paper, and what we looked at is, can we cluster people into different groups? And we found that, sure enough we can. Within the spaceflight group, there's a group of people, maybe around 8 out of 34, who are actually kind of proficient. They don't perform very well because they're disoriented, but nevertheless, they're showing learning across most metrics. They've sort of converged towards a strategy that's kind of optimal and that allows them to perform even given the limitations that they have. But more interesting is that we found a not proficient group, about 8 people who all converge towards the exact same suboptimal strategy. I call it suboptimal because this strategy makes them, as you'll see, go like complete bonkers crazy, but the benefit is that it does somehow reduce the number of times they hit the crash boundaries. So this was kind of really fascinating, and just so you can kind of see what it looks like, the top graph is proficient people who are again in the spaceflight condition. The black line is the angular position, the red line is what you want to concentrate on, it's the joystick. And you can see the joystick is quite varied and small deflections. But now you look at the not proficient group, and if you look at the red line, they're taking that joystick and they're just smashing it as hard as they possibly can. And it's just back and forth. There's very little variability in what they're doing with the joystick. It's back and forth, back and forth. So it's surprising that 8 people would converge towards the same exact strategy. Now, this is when I began to wonder, is there some way that I can mathematically quantify that the bad group has, or I should say the not proficient group has very little variability in the way that they use the joystick when you compare it to the position, the angular position of the machine. And that's when I reached out to Jonathan. Se-Wung also did similar stuff in a different motor system. And both of them sort of brought me to the Hilbert transform. Jonathan spent a pretty good amount of time sort of bringing me through what Hilbert transforms are and allowing me to understand it. And long story short, it did turn out that the variability in the phase difference between joystick deflections and positions were a lot statistically smaller for people who were not proficient compared to people who were proficient, who had a lot of variability in the way that they were doing the joysticks. Now, the underlying question is why? Why would they converge towards this? And one idea, a little bit of it's anecdotal because I kind of asked them. I can also kind of listen to what they're saying underneath their breath. And it turned out these individuals would typically be swearing a little bit more and be expressing frustration just underneath their breath, as I was listening to them. And so I reached out to this professor at McLean Hospital, and she studies anxiety and depression and stuff like that. And part of what we're going to do is look at quantifying levels of anxiety, other physiological measures, and see if that correlates with people converging towards this suboptimal sort of strategy. Yeah.
The reason why I say that you can just do that, because I think I would have done that. I didn't do the experiment.
Yeah.
But in a way, you're kind of controlling the randomness. You feel that, okay, I'm moving, I don't know where I'm going, so let me just do something that I know will stay at the center. Like you want to reduce the part of the falling that you don't control and you don't feel actually.
Yeah.
So by increasing and that's correlated again with the acceleration, angular acceleration, because you feel it.
Yeah.
Even in your back.
So
you're kind of removing. You're not doing it very well, but you're kind of removing the random, not the random component, but the component that you don't feel by controlling this.
It's a really great point, and
I think I would have done that. That's why I told you.
Yeah, so a lot of people may try it initially. That's why I call it a suboptimal strategy. It has some benefit, right? Because if you're flying around like this, you're kind of centered, so you're not doing the drifting behavior as much. And so you can stay up for longer. But the question is, well, why not then explore the solution space for other, slightly more optimal solutions? The idea being maybe people who have greater anxiety will just stick with one suboptimal strategy. So you probably would have tried this strategy, but eventually you would have been like, are there other strategies or other things that I can use that can allow me to balance a little bit better? But it's kind of interesting too, because you approach it from the mathematical viewpoint. Most people will not approach it from the math. They'll just sort of get into it and they'll be like, okay, I'm crashing a little bit less. I'm just going to stick with this. But part of what I've also been wanting to do in terms of collaboration is create sort of a rhythm and balancing game. And eventually we could put this on Steam and become millionaires. You never know. But because there is an interest for rhythm and balancing games, but create one that has a mathematical structure where you have multiple suboptimal solutions that a person can sort of converge towards and balance around, but only one optimal solution. And then look at the individual differences in how people explore this space and whether they just stick at one or go in different directions, and then see if it correlates to things like anxiety or performance in the machine. Well, those are some things that I've wanted to do. Okay, the final chapter is a fun one, but I think an important one. I call it partying. And the reason I sort of bring this up is I feel like it's important for academics to sometimes, break down these these walls that sometimes are very sterile and kind of just get a little bit dirty. in sort of like fantasy and like, and just like life and interacting with people and, some of these more creative stuff. So I'll give you some examples going from a little bit more conservative to a little bit more out there. So this first one, this was when I was a grad student. I had done this series that brought the Brandeis topology group with the Brandeis neuroscience group. And initially my thought process was, but we would sort of explore different topological, mappings as you go from, different sensory systems, or as you go deeper into one sensory system, from the eyes to the LGN, visual cortex, are there topological transforms, whatever, something like that. What we ended up doing, just as cool, was using graph theory to look at how neurons sort of branch, and that helped out a grad student in the Van Hooser lab. But I would be totally down, if any of you want to do, is take a mathematical subgroup, that's kind of what MathBio does, but take it and then mix it with some element of science that has not ever sort of interacted, and then see what connections lie there. And this was a diagram I had made for that. In a way, the math and the science, this was before MathBio seminar existed, so I was like, oh, this is a barrier, and here math and science, and we're trying to get together. But again, this MathBio seminar is beautiful because you guys are accomplishing this. The second sort of series I've been wanting to do for a while has been on universe building, because I think it's a thrilling topic that a lot of people are interested in. How do mathematicians do it? And from the very limited that I understood, like you could be like, here are a bunch of nodes, I'm going to make 3 assumptions on how you connect them, and then I'm going to see what kind of world or universe is created, and what are the properties of this universe. I think it's a cool concept. In neuroscience, you could sort of approach it from the standpoint of, here are a bunch of neurons, how do you manifest this universe of consciousness? From physics, you have like, how did the universe even start? And from mythology, of course, you have like, how do people think that all of this began? How does mythology work? So if you're interested in this series, I'm happy to organize it. It's been something I've been thinking about. The other sort of collaboration that I've been thinking about is educational outreach. And this is not only with like high school students, but for students that are way beyond high school. I say high school because I used to be a high school teacher. But a lot of my former high school students have come back and they're like, you know what, I'm really fascinated by math and physics, but I don't work with it at all. I don't know how to approach it. I'm afraid that if I say something and it's not real, then everything's false and bad. And I kind of want to create a space where people can just have fun, like mathematical fiction, or I don't know, like some exploration. So some way of making personality. So for example, like a series on how do you make your own number series. Like high school kids would probably love that. You go over some famous ones like the Fibonacci series or whatever, and then you say, here's how you can make your own, and then they custom make the Vivek number series or something. That would be fun. Or how do you create your own function? Or how do you create your own transform? Or your own like space, mathematical space? Like what are the requirements for that? Or your own coordinate system. I think we could have a lot of fun with that. It'd be kind of interesting. So if you're interested in that, let me know. And the last piece of this is the human augmentation partying. So this is an example of how like I party with different groups of people. And I'm happy to sort of organize this too. So this is all in my backyard. And this was on human augmentation. This was on human augmentation before I decided to make that my research topic. And most of my events have 3 components. The first is sort of reality, which is like presentations. So you had people talk about like VR and AR and drones and BCI and brain stimulation and AI, but then also things like yoga and chemicals and drugs and like transhumanism. And the second component is always art or discussion. You take those ideas from reality and then you meet new people and you sort of digest it through discussion, but also through some creation of something. And then the final component is doing something ridiculous, like a ceremony. And in this case, I'm giving birth to this mannequin that sort of, half of it represents humanity, half of it technology. And the question is, how do you balance these 2 parts, and how do you take what you learned from each of the 2 components before to bring these things together? So anyways, this brings like academics with people who are completely not academically inclined at all, but because it's so ridiculous, they come, they're interested, and then you have this sort of mixture of groups of people that don't interact. And I think that's kind of important and interesting. Okay, so that is that. So I will stop sharing, or maybe there's a question here. Okay, can you share your screen? Okay, cool. All right, so I think that is the end. Should I stop sharing, or should I?
I had a question. Could I take you back to the slide where you were sort of the first one where you were showing this drift in the experiment, the like back experiment.
Yeah, this one here.
Yes. Yeah. So I think when I look at this, I guess what I see is this sort of time scale of adaptation, where it does seem like if you look not at sort of this sort of fixed landmark, basically no deflection, but you think of that sort of landmark as having some memory, and so instead of being like absolute zero, it's kind of integrating over the recent past or taking some running average. Then you see actually, like in this trial, the subject actually does pretty well within certain time intervals.
Yeah.
So I'm wondering, like on the one hand, is that like adaptation time scale something that you could account for, where within sort of some time scale over which there's a memory of what that 0 point was, people can be doing better or worse, and that ties in a bit too with the sort of little vibrators. Like maybe there's also some time scale where if you did that on sort of a time scale corresponding to this natural memory, it might alleviate whatever sense of that conflict is.
It's a great idea. What's happening, and you sort of hit it exactly as it should be hit, is that like these people are converging towards sort of like a velocity strategy. So perceptually, when you're in this machine, you're losing sense of where you are, and you come back each time, you feel like you're at the 0 degree point, but you get better and better at sort of reducing your velocity, which is why your oscillations get tighter and tighter. In the phase space, they get sort of smaller and smaller, and what then begins to happen is it's as if zero velocity, like that moment where you sort of come back and it's sort of stationary, it sort of almost makes you feel now you're at the 0 degree point. So yeah, I mean, like if we look at that behavior, and I've sort of looked at it by just characterizing velocity and being able to explain it to the phase plots, then you're right. Like they are definitely learning something, because the number of times they hit the crash boundaries also goes down as a result of this better control. Yeah.
Because I guess part of what I'm wondering is if what you're asking is even sort of a possible task. I mean, if you take away all of the sensory cues, I guess what you're saying is in the literature it says it should be possible because you have some circuits that can integrate. But I guess I'm a little skeptical that those circuits are so reliable. And what seems to me more likely is that there is some kind of memory where I'm not going to remember, like I'm not going to be able to integrate from the beginning of this simulation, but I can remember something on a shorter term. I think part of what I'm just wondering is even like the people who you said there was a subset that really do well. I'm wondering if maybe you actually don't really understand the reason why they do well. Like maybe they find a landmark somehow. Maybe they're like, those are the people who are able to like see through the blindfold in some way. I guess I'm wondering.
No, it is. It's a really good point.
Are you asking for something possible?
So they do find a landmark, but it's a little bit of a trick. So I can balance on the back, and most people in the lab can sort of do it to a certain extent too. And what it consists of is that and I developed a training program to sort of like enhance people's ability to do this. The first sort of realization is that if you're still, velocity equals 0, that doesn't mean that you're at the balance point. That's like the first big thing that you have to sort of have the epiphany of. And then the next one, the trick is sort of like you sort of are paying a little bit more attention to the way that you're falling. So, if you sort of pushing yourself, like Jonathan, you said, you're always falling in the same direction. So if you keep pushing yourself and then you fall to the opposite direction, all of a sudden you've passed the balance point. And then, and again, some people are able to do this without even being able to articulate it. But essentially what they're doing is that they're straddling the balance point and sort of following kind of equally to the left and right. And once you can do that, then you're always going to be at that balance point. And you don't really need to actively think. But that's sort of like the people, because I asked them, like the people who are able to do this task, that's what they're sort of focusing on, and they're able to do it. That's a trick that you probably can't use if you're like in spaceflight or something like that. So then the vibrotactors, the hope was that you can sort of use that, because now you do have positional cue to be able to do it. And some people are not able to ever overcome this inability or like this feeling that they're somewhere different than what the vibrotactors are telling them. It's great insight though, without even being in the machine. Alberto, yeah?
Yeah, just wanted to add that even if you find this heuristic that works for yourself, you're still not immune from the illusion. So you are able to balance, but you're not, like you still feel the drifting or you still feel the disorientation. So it's, what Vivek is studying is not limited to how you can do the task of balancing. It's also the other
Perception of
condition.
I wanted to comment that this idea of having this conflict between the data coming from the vibrotactors and your perception of where you are, that's a classic case in flying aircraft. Normally, you can look through the window and the horizon is the primary cue for orienting the airplane. But if you fly into clouds, instrument conditions, you have no visual reference anymore. And in 25, 30 seconds, most pilots, without training, will get into a death spiral, and that's it. So in instrument training, the way they resolve this problem is you are constantly trained to listen to only the instruments and ignore your perceptual feelings. That's the way you resolve that.
Yeah, and Joel's a pilot, by the way, too. So this is.
So it's just that's something that you don't normally do, is ignoring your senses, but you have to ignore them, and it's so compelling, and it's difficult at first to ignore them.
Yeah.
Because you think the instruments are failing.
Yeah. It's,
So pilots in military planes, sorry,
no, please.
but they also get disoriented from the acceleration, right?
Yeah, pilots are killed every year by spatial disorientation. Every year they have.
And that's not only because they don't perceive their position, but also because you lose some kind of blood to your head. I mean,
No, that's totally different. Like, remember, you can interpret acceleration can be interpreted as tilt. So the classic case is a pilot, is landing in instrument conditions, and there's a point where it's called the missed approach point, where you can't land, you can't see the runway, you can't land. So you apply full power, go around. Okay, when you apply full power, you feel like you're pitching up. All right, and so pilots are trying to fly level. They push the stick forward and fly right into the ground. There was a famous case it's happened in Canada in an airliner where a pilot was making an approach in instrument conditions like that, and he couldn't see the ground. He decided to go around, so he applied full power, and at that very moment he was able to see out the window patches of the runway, and the pilot in command was looking at that, and subconsciously, because of that illusion, tilt illusion, he pushed the stick forward. The co-pilot was only looking at the instruments. The co-pilot said, descending, because he was looking at the instruments. The pilot was in command, continued to descend, and then the co-pilot said, with more emphasis, descending. The pilot in command did not respond, flew that airliner into the ground, and killed everyone. So after that, you see, at that point, the captain had control. His authority was not challenging. That accident ended all that. Now it's the co-pilot, it's cockpit resource management, they call it. Anyway, everybody has an input. The captain is no longer dictator. But that illusion kills people to this day, every year.
Vivek, in the spaceflight condition, you said that 8 people did very good performance, 8 people did bad. So I'm curious about two things. How many how well, the good performance, how much time did they take in trial space or trial metric to reach the good performance? And what about the others out of 34? What did they do? A mixture or?
It was a mixture, so we sort of clustered people together, and so yeah, I mean it was maybe a little bit less than 8, around 8. In terms of how fast, so we used like the machine learning algorithm to predict how. So these experiments were 2 days, in a row, like an hour each. So there were like 40 trials, and we didn't really get like good prediction until like I think it was maybe like 10 trials in or something. So yeah, it wasn't like
About
super.
a quarter of
Yeah,
total exposure.
yeah. Before they sort of converged at like what they're going to do.
Did you do any experiments on pilots or people did that? I mean, people who are used to be disoriented and.
Yeah, so not a lot. I haven't done any military paths, but I've done like aircraft, like gliders and like whatever the small planes. I forget what they're called, but they don't really perform that much better. I don't know if they've gone through orientation training, but even if they have, because they don't have any meters in front of them, they don't have any like particular advantage. They may perform better with vibrotactors. I haven't done that yet. So, yeah, I've ran like gymnasts too, and like dancers and stuff like that, and I haven't found too much of a difference.
In the vibrotactor, you have to tell them to focus on the vibrotactor, or they eventually manage to?
The people who don't go through the training, even if they know that the vibrotactors are working, how they're working, the fact that they're disoriented, so they'll say, I know I'm disoriented, have a 100% belief in the vibrotactor to tell me the right thing, but they're just not able to use it. The people who go through the training, and the training is you're in the upright, you don't know where the balance point is, so you have to listen to your vibrotactors in order to get to that balance point. So people who go through that, then they're able to apply it a lot better, and then they show learning on the second day when they're in the spaceflight condition. Yeah.
It's very hard to get rid of your illusion.
It's very compelling. What internally, you
Without
grow up.
training.
Yeah. I mean, you were born with it. You respond to it. So, yeah. Cool. Well, thank you.
Thank you.
How do I turn my camera off?
The acceleration.